Alright folks, here we are today talking about acid-base titrations. Now you're going to find lots of videos out there on the internet on how to do these titrations and maybe even a couple on how to do the calculations. But I want to go through the three examples I've given you, those three types, and one of each involving the three uses that we use to use titrations to calculate. So the first one is calculating an unknown solution concentration. The second one will be percent purity, and the third one is figuring out the molar mass of a situation. Okay. Now, one thing I want to talk about here before we get into these is going to help us out a little bit when we're talking with these calculations. If we are talking the value molarity, we know this as being moles per liter. Okay. But when we're dealing with a lot of these calculations for titrations, we're dealing with milliliters, okay? And so we can do that conversion from liters into milliliters and vice versa, or we can also look at this and say that millimole per milliliter, okay? 1 mole per 1 liter, okay? Well, there's 1,000 millimoles in a mole, there's 1,000 milliliters in a liter. So these values are the same and they will make our calculations a little bit easier. Okay. If we're having any trouble with this, any confusion at all, do switch back to this moles per liter. I'm going to use both. Okay, I'm going to use moles per liter in our first calculation and I'm going to use millimoles per milliliter in our second calculation, just to show how easily they are interchangeable. Okay. Our first example is 25.00 milliliters of H2SO4 requires 46.23 milliliters of 0.203 molar sodium hydroxide. Okay, and we want to figure out what's the concentration of this H2SO4 that we started with. Okay, well, this isn't too bad. This is the types of calculations we've done before. Hopefully we've seen these in Chem 11, and we've done similar type calculations in previous units. First thing with any of these types of calculations is let's write out our balanced equation. Okay, so it's the hydroxide and the hydrogen from here is going to form the water. We have the sodium and the sulfate forms sodium sulfate. We just got to balance this out, and that would leave us with 2 and 2. Okay, so this one we do have a molar ratio that we've got to be careful with, and we'll see that in the steps. All right. Well, I want to take this 46.23 milliliters, so I'm going to say this is 0.04623 liters. Okay, and that's our NaOH. Okay. We're going to multiply this by our 0.203 moles per liter. Again, this is our NaOH. Okay, and if I multiply this by our 1 mole NaOH per, 1 mole of H2SO4 for every 2 moles of NaOH. Right, so these liters are going to cancel out to leave us with moles of sodium hydroxide. Okay, and then this calculation takes our moles of sodium hydroxide and turns this into moles of sulfuric acid. And so this gives us 0.004692 moles of H2SO4. Okay, so we had to use up this volume at this concentration of sodium hydroxide required this many moles of sulfuric acid, and this many moles came in 25 milliliters. So to figure out my concentration of my H2SO4, I'm going to take my 0.004692 moles divided by my 0.02500 liters of solution. This gives me a concentration of 0.188 molar. 4 sig figs, 4 sig figs, 3 sig figs. 3 sets the tone, 3 sig figs in my final answer. Okay, so that is figuring out the unknown concentration from a known concentration and the volumes that we had. Okay, let's move on to figuring out percent purity. All right, folks, next up we're going to talk about percent purity. Okay, we have 2.70 grams of strontium hydroxide in 250 mils of solution. We take 25 mils of this above solution, okay, and we neutralize that with 31.39 mils of hydrochloric acid. Okay, so let's say we take 25.0 mils of that is needs, what's the volume here? 31.39 milliliters of 0.131 molar hydrochloric acid. Okay, and we want to calculate the percent purity of this value. Okay, so we want to make sure that we remember that percent purity equals the actual value divided by the expected. Multiplied by 100%. Okay, so we've got to figure out both the, and this actual is also known as the experimental. Okay, what we actually got from the experiment versus the expected, which is our stoichiometric or our theoretical values based on the numbers that we had. Okay, so we got to figure out both of these, both the actual and the expected. Okay, then we can plug these into our equation here and figure out that percent purity. All right, so actual. Oh, and one more thing before I actually calculate this. Let's take our equation here. Okay, so we've got this on here. We have our calculation. We need to balance those out. We're going to have 2 waters and 2 hydrochlorics. Okay, so that's just important when we do this stoichiometric value and see what we actually get. Okay, so our actual concentration. All right, well, we take 31.39 milliliters of our HCl. We times that by our millimoles per milliliter. Okay, so this one I'm not changing. I just take that concentration, that 0.131 moles per liter, or millimoles per milliliter. And again, this is still HCl. Okay, and then I'm going to multiply that by, we've got 2 moles of HCl for every 1 mole of SrOH2. Okay, so 31.39 milliliters of hydrochloric acid times by our concentration divided by our molarity. This leads us to having 2.056 millimoles of strontium hydroxide. Okay, so we got that many millimoles. Now that was in 25 milliliters. Okay, so if I'm looking at this concentration of this SrOH2, I'm going to take my 2.056 millimoles, and that was in 25.0 milliliters. Okay, so this gives me an actual concentration here of 0.08224 molarity, right? Millimoles divided by milliliters still gives me that molarity. Okay, so there's the steps to get the actual value of that concentration. So I'm just going to get this out of the way for a second, rewrite this actual value. Okay. Now our expected value for our concentration of that SrOH2 is, well, I took my 2.70 grams, and that was in 250 milliliters, so 0.2500 liters. But now again, this is concentration in grams per liter. We had in moles per liter. So I've got to multiply this by the inverse of the molar mass. And for strontium hydroxide, that is 126.1 grams per mole. This will give me moles per liter, or concentration, and our expected value is 0.08565 molar. We now have our actual, we have our expected. Okay, I'm just going to rewrite this a little bit. Remember, our percent purity is our actual divided by our expected. So I take that actual value that I had, divided by this 0.08565 molar, and I times that by 100%, and I get 96.0% pure strontium hydroxide. Okay. So once again, we use the data from here to figure out the actual concentration based on this line here. The 25 mils needs this 31.39 mils of 0.131 molar. That gives us the actual, the experimental value, whereas we can get the expected from the fact that we took the 2.7 grams in 250 mils. We should have had this value. We take the actual over the expected times 100% to get that percent purity. Okay. Hopefully that helps. One more example to deal with, determining the molar mass. All right, last example here for titrations. We're going to talk about how to figure out the molar mass. Okay, so for this one, we have 2.73 grams of a diprotic acid. Okay, diprotic means two hydrogens. Okay, so we take this 2.3 grams of whatever this acid is, and we make a half a liter of solution. Okay, so once we have that, we're going to take 25 mils using a pipette, so an accurate 25.00 mils of this above solution. This is going to need 30.5 milliliters of 0.1112 molar potassium hydroxide to neutralize it. Okay, so once again, we're going to start off with our balanced equation. We've got this H2A plus KOH. Well, potassium has a charge of +1. This acid obviously has a charge of -2, so we're going to go K2A. And then for each hydrogen, we need a hydroxide, and so that's going to give us our water. And again, we're going to have this 2-to-1 ratio. Okay, something we're seeing a lot in these titrations, but not as much in our KAKB. Hint, hint. Okay, we now need to figure out what the molar mass of this is going to be. So let's figure out the number of moles of acid we have, and then we can figure out our concentration. Okay, so I needed this 30.5 milliliters, and I want to find out the number of moles of H2A that I can get from that. So we're going to take this 0.0305 liters of potassium hydroxide multiplied by our concentration, moles per liter. Okay, and then we're going to multiply that by our molar ratio. So right now, when I've done this, I am now in moles of potassium hydroxide. So I need to put my 2 moles of KOH in the bottom, and that leaves me with my 1 mole of my diprotic acid on top. Plugging all this in, this gives me 0.001708 moles of the diprotic acid in this 25 milliliters. Okay? So we can then use this to get to the concentration. Okay, so we're going to use that to get the concentration of this H2A. Okay, so the concentration of H2A is going to be this number of moles in my 25 milliliters. Okay, and so this gives me a concentration of 0.06832 molar. Okay. Well, now this is moles per liter. So you can get rid of this stuff here now so we can work on. So I've done all of this to figure out the concentration of this solution that I made. So if I take my 0.06832 moles per 1 liter, and I multiply that by my 0.500 liters, this gives me the number of moles I had from this acid. And that gives me 0.03416 moles. Okay. Well, remember, molar mass is just grams per mole, right? Molar mass, grams per mole. So if I take my 2.73 grams of diprotic acid divided by the fact that that was 0.03416 moles, this gives me 79.9 grams per mole for this unknown diprotic acid. Okay, that brings us to the end of our titration section, and in fact the end of our acids and bases. If you have any questions, please post those in our chat room, and I'll get back to you on those as soon as possible. Take care, folks.